Swayam Prabha. Digital India. Educated India.
Welcome back to the video course on fluid mechanics. In the last few lectures, we were discussing about the introductory theories on fluid mechanics, introduction to various fluid properties, and then we discussed about fluid statics, its related theories, and then we have discussed about buoyancy, pressure, fluid pressure, center of pressure, meta center, etc. So today we will discuss another topic, fluid kinematics. So the main objectives of the topic on kinematics of fluid flow is to introduce various aspects of fluid motion without being concerned with the actual forces necessary to produce the motion. Then the other objectives of this topic are to introduce the kinematics of the motion, the velocity and acceleration of the fluid, and the description and visualization without considering the force, and then we will introduce the fluid dynamics, and finally to understand the fluid motion through the kinematics of fluid flow. So that is the important objectives of this section on kinematics of fluid flow. So as we have already discussed, the kinematics of fluid flow means, say, the fluid flow is taking place due to various forces, but when we consider the fluid motion, say here in this kinematics of fluid flow, we will not consider the forces as such, but without considering the force, what happens to the fluid or how the fluid is moving, say how the velocity can be calculated, how the acceleration can be calculated, and then we will go to the various say the principles of fluid mechanics, like conservation of mass, conservation of momentum, based upon the fluid kinematics. So if you consider the various examples of fluid motions, like the smoke emerging from a chimney, or the flow of the atmosphere as indicated by the motion of clouds, or the motion of waves in a lake. So all these fluid motions, say here generally when we try to analyze all this fluid motion, say there can be considerable insight to this fluid motion, say by considering the kinematics of such flows without being concerned with the specific force that drives them. So the smoke emerging from a chimney, there is a force which is say taking place, which is driving the, or which moves the smoke, or say the wind or the atmospheric motions or the motion of clouds and or the waves in a lake. All these, there are some forces, but the analysis will be much simpler when we consider this say fluid phenomena or fluid motion without much concern to the specific force that drive them. So that is the importance of this kinematics of fluid flow. So we will be considering this session the kinematics of fluid flow with respect to these various fluid motions, so without giving much attention to the force driving this say the driving force which due to this the fluid is moving. So say we will be considering the various aspects of kinematics of fluid flow, starting from the velocity field, and then we will discuss the Lagrangian and Eulerian concepts, and then we will discuss about the acceleration field, etc. So now say the fluid parameters by field representation, as I mentioned earlier, the fluid movement is, say, when you consider the fluid movement, the movement is, say, in with respect to space as well as time. So if you consider the space, say when we consider the three-dimensional motion of a fluid, so with respect to x, y, z axis, and then time t will be also will be there. So the fluid motion is with respect to space and then with respect to time. So the fluid parameters are generally represented by the space, say the space coordinates x, y, z, and then the time t. So for example, as shown in this figure, say here, say the fluid is moving, say in a pipe or in an open channel. When the fluid is moving, so the motion is with respect to space and then with respect to time, so that we can represent, as shown in this figure, the velocity field can be represented as, say, v is equal to, say, u x y z t of, say, I the unit vector, plus v x y z t of the unit vector j, plus w x y z t with the unit vector k. So since the velocity is say it has got a direction as well as magnitude, so that we will be representing generally with respect to I, j, and k, which are the unit vectors, and then u here u, v, and w are the magnitude of the velocity movement, and finally the velocity field can be represented as v is equal to u I plus v j plus w k, where u, v, w are dependent upon the spatial coordinate x, y, z and time t. And then finally the speed of flow we can represent, say, when we are considering a pipe flow, or when we are considering an open channel flow or any kind of flow, we can represent the speed of flow as, say, it will be the absolute value of this v, it can be represented as square root of u square plus v square plus w square, as shown in this slide. So the speed of flow is, say, square root of u square plus v square plus w square, that gives the speed of flow. So the velocity field is generally represented as the function of spatial coordinate x, y, z and time. So here you can see that a particle is moving from a position A to say another position. At time t the position is here, and at time t plus delta t the particle is moving from this position to the new position. So that here this position vector, we can, if you draw the position vector, so this RAT is the initial position vector, and then RAT plus delta t is the present position of the fluid particle. So with respect to this, the particle is located in terms of the position vector, and then with respect to this only we will be describing the movement of a fluid particle in any fluid media. So when we represent the velocity, say here this position will be with respect to x, y, z coordinate and time, the current time here, and then the new position will be also represented in terms of the new position x, y, z and then time t. So the particle location in terms of the position vector. So here, say in this slide you can see that a velocity field, say for example, say in a river there is a flow takes place. Here you can see that, say the flow is say with respect to various flow conditions, the flow can be this direction or the other direction. So the flow velocity vectors, say the velocity vector is, we can represent with respect to spatial coordinate x, y, z and also with respect to time. So here this figure shows the, say actually this figure here some contamination or some plume is introduced in this river system, and then how it is moving. So with respect to that, generally we will be solving for this kind of problem, we will be solving first the hydrodynamics or the velocity we will be determining, and then with respect to that the velocity only we will be describing the contaminant movements or the plume movement we will be describing with respect to the velocity vector. So it is very important that we should know the velocity field, that means with respect to space and with respect to time, so how the velocity is changing, that is very important. That is actually the major problem as far as fluid dynamics or the fluid flow is concerned. The velocity field or the velocity determination with respect to space and time is very important. So as you can see in this slide, and then also the velocity field we can say with respect to particle flow trace, we can trace as shown in this figure. We can trace the particle, say how it is moving, say with respect to either path line or with respect to either streamlines. We can represent the velocity, the flow, how it takes place, and then we can represent as shown here. They say this is actually a river system joining an estuary. So how it is behaving with respect to the velocity field we can represent with respect to the path lines and streamlines, and as shown in the previous slide we can also use velocity vectors to represent the velocity field. So now, as I mentioned, so here we will just discuss a brief example problem how to determine the velocity field. As I mentioned, since velocity is say varying say with respect to x, y, z direction, so that say we will be determining the velocity field with respect to the x, y, z coordinate as well as the time. So the problem here is the example problem here is the velocity field, the velocity in a flow field is expressed as v bar is equal to the velocity vector is equal to 7t plus 2xy I, the unit vector I, plus minus 2yz minus 4t unit vector j, plus minus yz plus z square by 8 unit vector k. So this is the velocity field is represented by this function given with respect to I, j and k. So say the magnitude in x, y, z directions are represented by, say, this quantity gives the x direction, that means velocity component u is given by 70 plus 2xy, and the velocity component in y direction v is given by minus 2yz minus 4t, and the velocity component in z direction w is represented here as minus yz plus z square by 8. So we want to determine the magnitude of velocity at a point q. The position of q is x equal to 3, y is equal to minus 1, z is equal to 2. So at time t is equal to 3. So the coordinate system, say x, y, z is given here, and time also given. So we want to determine the magnitude of the velocity at a point x equal to 3, y is equal to minus 1, z is equal to t at time t is equal to 3. So here the function, the velocity field is represented already given by this v is equal to this function. So this we can represent say as a vector, say as we have discussed, say the velocity can be represented as the velocity vectors u, v, w, and with respect to the I, j, k triad as u, I plus v, j plus w, k, where I, j, k are the unit vectors in x, y, z direction, and u, v, w are the velocity in x, y, z direction. So here v is represented, and as I mentioned, u is here with respect to the given equation for velocity field. U is 7t plus 2xy, and v is minus 2yz minus 4t, and w, the velocity in z direction, is minus yz plus z square by 8. So the position of the point is already given, x equal to 3, y is equal to minus 1, and z is equal to 2, and the time is also given as 3. So that now we can determine the magnitude of velocity in x direction. uq, we will substitute this value of values here in for u, so that we can write uq is equal to, that means the velocity component u at point q is say 7 into time 3, t is equal to 3, so 7 into 3 plus 2 into 3 into minus 1, so that will give 15 as the result here. So uq is equal to 15, and then vq, that the velocity in y direction at point q is given as vq is equal to minus, say here the value is minus 2 yz minus 40, so minus of 2 into minus 1, since y is minus 1 in time is t, z is 2, so minus 2 into minus 1 2 plus time is 3, so 4 into 3, so that will give vq as minus 8. So similarly we can determine wq. So wq is given as minus yz plus z square by 8. So that is, so if you substitute for y and z, so y is minus 1, so minus of minus 1 into 2, z is 2, and then plus 2 square by 8, so that will give the value of 2.5. So finally, as we have seen, the velocity can be, the magnitude of the velocity at the point q can be determined by taking square root of uq square plus vq square plus wq square. So here it is vq, the magnitude of the velocity is equal to square root of say 15 square plus minus 8 square plus 2.5 square, that is equal to square root of 295.25, and that is equal to 17.18. So its corresponding units can be put here, say either meter per second or centimeters per second, depending upon the problem. So like this, say the velocity can be represented in x y with respect to the space x y z, and then time, and then if you want to determine the new position of the velocity, if the function the velocity variation as represented in this figure is known, then we can determine the magnitude of the velocity. So this is the velocity field. So here the velocity can be represented with respect to space and time. So like this, the velocity field is determined. Now we will discuss about the flow field description. So in the introductory lecture, we have seen the various aspects of how a flow field can be represented. So there we discussed about two kinds of fluid flow field description. So first one is one was Eulerian description, and second one which we discussed was Lagrangian description. So here further we will discuss, since we are now discussing the kinematics of fluid flow, so further we will discuss these two description, fluid flow description. So first one is the Eulerian description. So as we have seen earlier, so the Eulerian description uses the field concept. So as we have already seen the velocity field or the acceleration field or the pressure field, whatever it is. So here the Eulerian description uses the field concept, and the fluid motion is given by completely prescribed the necessary properties such as the fluid properties such as pressure, density, velocity, etc. as functions of space and time. So as we have already seen, the velocity here is represented as a function of x, y, z coordinates and time t. So in the Eulerian description, the fluid motion is given by prescribing the necessary properties. Say properties can be velocity or pressure or density, whatever it is, as a function of the space and time. So now if you use the Eulerian description, say from this method you obtain the information about the flow in terms of what happens at fixed points in space as the fluid flows past those points. So what we will be doing, say if you consider the fluid motion in a say in an open channel or in a pipe flow, say for example let us consider a river flow here. So this is a river flow. So what we are doing here is, say with respect to, say the flow is taking place all the time. So now we will be considering a particular section, say here 1 or say section 2, and then say between this section 1 and 2 what happens, say to the various fluid flow properties like velocity, how it is changing, or how the pressure is changing or the various other fluid flow parameters are changing. So that is what we are generally describing in the Eulerian description. So generally saying most of the fluid flow problems, as we have discussed earlier, we will be generally using Eulerian description. So from this we are getting the information as say as the flow progresses, say in terms of what happens at fixed point. So here the fixed point which you are considering this section 1 or even it can be a fixed point or it can be a section like this. So with respect to this, what happens for the fluid properties, say when the fluid flow is moving from say one section to another, or at that particular section with respect to time, what happens to the fluid flow. So that is the way which we will be describing the fluid flow in the Eulerian description. So here you can see in this figure, say here a river flow takes place and the concentration, higher concentration or the contaminant bloom is introduced at this position. And then if we want to see in the Eulerian description, what we can do is say there can be an observation point as shown in this slide. There can be an observation point like this, and then say what we will be describing is when the river flows takes place, say with respect to time, say we will be checking what happens, whether the contaminant, the concentration is in, say how it is varying with respect to say this particular section with respect to time, how it is varying. So if you plot this for this particular position, then you can see the contamination, the concentration will be reducing as the flow proceeds like this. So this graph shows how it will be behaving. So this shows the Eulerian description in fluid flow. So as we have discussed earlier, so generally the Eulerian description is very much useful in fluid mechanics, and most of our fluid flow analysis will be based upon the Eulerian description. And the second method which we have discussed earlier is the Lagrangian method. So the Lagrangian method, as I have mentioned, so in the Lagrangian method, say we will be following individual fluid particles. So what I say, if a fluid flow in an open channel or in a river flow or in a pipe flow, then what we are discussing is say if this is the flow or river flow, then say we will be chasing a particular particle. So then with respect to this say t is equal to 0, then say t is equal to t1 or say t is equal to t2 or then t is equal to t3. So like that, what happens to this particular fluid particle? So that is the way which we are chasing out in the Lagrangian method. So Lagrangian method, we follow the individual fluid particles as they move and then determine how the fluid properties associated with these particles change as a function of time. So this is mainly with respect to time what happens, and the position is anyway with respect to fluid particle movement, it is always changing. So the one particular fluid particles are traced, and then what happens to those particles. So that is what we are doing in the Lagrangian method. So here the fluid particles are tagged or identified, and then say as time progresses, what happens to those particles. So that is what we are describing. And since as you can see that fluid motion or fluid flow is concerned, it is very difficult to track individual particles like this and then see what happens to those particles. So generally this Lagrangian method is very rarely used in fluid flow problems due to its difficulty to track a particular particle or to tag a particular particle, and then what happens to that particular particle. It is very difficult to do this kind of say analysis. So generally for most of the fluid mechanics problem, Eulerian method is used since it is much simpler, and then we get the information what we are looking for, say especially at particular sections with respect to time we are getting. So that is most of the time we will be using Eulerian method in the fluid mechanics or fluid flow analysis. So finally in this slide, so here this slide shows how the Eulerian approach and Lagrangian approach is used as far as fluid flow analysis is concerned. So here, so you can see that say the fluid is moving say from a from a section, a channel like this. So here, say in the Eulerian approach, say we are taking, say, considering a particular point at a particular section here like this, and say the point is at a, from this phase x at a distance of x0 and y0, we are considering a particular point, say the location is t is equal to t, x0, y0, t. So what happens to fluid flow as far as this particular point is concerned? So that is we will be studying in the Eulerian approach. So this will be generally with respect to time, how the fluid is behaving. But as far as Lagrangian approach is concerned, here you can see it is mainly with respect to time. So we have only tracked one particular particle, and then from this position to this position how it goes, or like that we are chasing out the particular particle, and then we are describing the flow properties with respect to the properties for this particular particle is concerned, and that is the Lagrangian approach. So even though we rarely use Lagrangian approach, but once the fluid flow parameters are known, we can convert into Eulerian description, or from the Eulerian description to Lagrangian description also the conversion is possible. So now let us discuss a small example how we can utilize this say Eulerian approach and Lagrangian approach as far as fluid flow field description is concerned. So here the problem which we are discussing is, say here the flow field description. So in an experiment of flow experiments we are conducted in laboratory flow. So the two-dimensional flow in a Lagrangian system is already obtained as x is equal to x1 into e to the power lambda t plus y1 into 1 minus e to the power 2 lambda t. So where lambda is a constant and t is time, x is the x-axis, say here with respect to x, and then with respect to y, and then time. So this is a two-dimensional problem. So the fluid flow properties are changing with respect to the space xy and xy direction and time t. So here say already the two-dimensional flow in the Lagrangian system is given as x is equal to x1 into e to the power minus lambda t plus y1 into 1 minus e to the power 2 lambda t, and also for y direction is concerned, it is given as y is equal to y1 into e to the power lambda t. So this y1 and x1 indicates what is the initial position. So this is x1 y1, and then say the variation with respect to x and y are given with respect to time t by this equation number 1 and then equation number 2. So we want to find an expression for path line of the particle with respect to this Lagrangian system given, and then we want to get the corresponding equation in Eulerian system velocity components we want to determine. So the problem is we want an expression for path line of the particle and then Eulerian system velocity components. So this we can solve. Say first the first problem is we want to find the path line for the particle. So path line means say it should be an expression without any time. So we will use this equation number 1 and 2. So we will eliminate t, the time component, to get path line. So from the second equation, so from second equation we will get e to the power lambda t is equal to y by y1. So the equation is given as y is equal to y1 into e to the power lambda t. So from that we can write e to the power lambda t is equal to y by y1, and then this e to the power lambda t is already there in equation number 1 here. So we will substitute back for this e to the power lambda t in equation number 1 here for the expression for x. So we will get x is equal to x1 into y1 by y, since e to the power lambda t is already obtained as y by y1. So e to the power minus lambda t will be y1 by y. So x is equal to x1 into y1 by y plus y1 into 1 minus y1 by y or square. So this gives the expression for the path line description of the particle in the Lagrangian system. So see here there is no time component is involved. So this gives the expression for path line of the particle. So now The second part of the problem is we want to get the Eulerian system velocity component as far as this with respect to the Lagrangian system given. So, in the Eulerian system the velocity component we can write as, so since the Eulerian system which we have discussed this as here you can see that at a particular position what happens, so that gives the velocity component. So, here with respect to this slide here we will get the velocity component ux is equal to dx by dt and uy will be dy by dt. So, that means velocity in the y direction will be dy by dt and velocity in x direction will be dx by dt. So, we will just differentiate this equation number 1 here given here, that if you differentiate that will be the velocity component in the x direction. So, we will differentiate the equation x is equal to x1 into e to the power minus lambda t plus y1 into 1 minus e to the power 2 lambda t. So, if you differentiate ux is equal to dx by dt, so that is equal to d by dt of x1 into e to the power minus lambda t plus y1 into 1 minus e to the power 2 lambda t. So, now from this if you simplify, if you differentiate and simplify, you will get an expression for velocity, that is the Eulerian system. So, ux is equal to minus lambda x plus lambda y into e to the power minus lambda t plus e to the power minus 3 lambda t. So, here this after differentiation we will simplify, finally we will get the expression for velocity as ux is equal to minus lambda x plus lambda y into e to the power minus lambda t plus e to the power minus 3 lambda t. So, similarly, the velocity component in y direction we will get uy is dy by dt. So, that we can just differentiate, since the initial equation the expression for y is given in the Lagrangian system as y is equal to y1 into e to the power lambda t. So, if you differentiate we will get ui is equal to dy by dt, that is equal to d by dt of y1 into e to the power lambda t. So, that is uy is equal to lambda 1 into y1 into lambda into e to the power lambda t. So, that will give this can be written as, say, since y is y1 into e to the power lambda t. So, uy can be written as lambda y. So, that gives the expression for the velocity component in y direction for the Eulerian system. So, like this, if the velocity field or any particular fluid flow parameters is known in one system, either in Lagrangian system or in Eulerian system, then we can convert to other system with respect to the various mathematical relationships available with respect to both the system. So, now we have seen how we describe the various fluid flow properties with respect to two description, the Eulerian description and the Lagrangian description. So, as I mentioned, generally we will be using the Eulerian description, since it is much easier and it is easily the analysis is much simpler and we can get results, especially since in fluid flow we will be much bothered about what happens to flow at particular sections than just tracing some fluid particle. But in some cases also, some problems we will be taking the Lagrangian approach by tracking a particular particle. So, that will be also discussed later. So, now with respect to this say the field description. So, now the fluid flow as we have discussed earlier can be described, say now briefly we will again review this fluid flow description. So, space wise, as I mentioned, the flow can be either one dimensional, two dimensional or three dimensional flow. So, the flow, as I mentioned, generally all the flows are three dimensions in nature. So, it is varying with respect to x, y and z and also time. But say many of the problems, say for example, as I mentioned when we discuss a river flow, so if you want to know say particular with respect to the longitudinal direction, say L, or here in this x direction. So if you want to know with respect to this longitudinal direction what happens to the flow properties like velocities or the head or the pressure or other parameters, then it is better that we consider the fluid flow as one dimension, or say when we need more details the same problem we will be describing as two dimensions, so that this x and y both components we will be describing, so that the velocity in the lateral directions in u and v will be also considered, and then correspondingly the time and then the other parameters will be considered in two dimensions. And otherwise if we are looking for much accurate say description the analysis, and then if we are looking for a problem in three dimensions, so that we have to consider say for example the flow in a river is concerned, so here we have to consider the depth wise also. So what happens with respect to z direction, so not only the longitudinal, the lateral, plus we have to consider the depth wise also. So depending upon the problem, so but most of the fluid flow is concerned it is three dimensional nature, but we will be simplifying the problem into one dimensional or two dimensional, three dimensional problem. So as you can see here, here say it is a river flow. So here this slide shows what happens with respect to the flow. So here the analysis is say various section we are considering, and then analysis is say with respect to this one dimensional say what happens. So space is only one dimension, and then with respect to time, so the variation is with respect to this the length of the river. So here with respect to x and then time we will be analyzing. So this is especially in one dimensional flow is concerned, we will be analyzing with respect to what is happening in 1D. So this is fluid flow in one dimension when we analyze as one dimension. And then the next here this slide shows the space is 2D. So what is happening with respect to two dimensions? So that is why all this here in this blue, this with respect to what happens in y direction laterally also we have considered. So that is why here the spatial wise this is two dimension flow which you are considering. The flow is definitely three dimension, but we are simplifying the flow to two dimension, and then we are analyzing as a 2D flow or two dimension flow. And then next here you can see the space is a three dimensional flow. So here the depth is also considered in a flow, and then with respect to the length of the channel and then lateral direction. So it is a totally three dimensional flow. So depending upon the necessity or depending upon the type of problem which you are dealing, the fluid flow analysis can be one dimensional, two dimension, or three dimensions. And then also as we have discussed earlier, the time wise say the flow can be say most of the time the flow will be varying with respect to time, but many times we can also say that once there is not much variation with respect to time, then we can consider there is no variation with respect to time for the fluid properties, then we can consider as steady state flow. So with respect to time we can consider the fluid flow as steady state flow and unsteady state flow. So in unsteady state flow definitely the fluid flow properties are varying with respect to time. So we have to see the spatial variation as well as the time variation. But as far as steady state flow is concerned, so we will be discussing with respect to spatial direction only, since time wise it is steady state. And also we have discussed say generally to describe the fluid flow we will be using various fluid visualization, flow visualization techniques, and also certain say lines like streamlines, streak lines and path lines are generally used for to describe the fluid flow. So this we have already seen in the previous slide, say how we are using this kind of analysis as far as the fluid flow description is concerned. So here you can see the path lines are used, and also streamlines are used for the velocity description, and here the streamline, the velocity vectors are used, and with respect to the velocity vectors we can find out the streamline. So the streamlines, path line, streak lines, which we have already discussed in the introductory chapter. Streak lines, all these lines are also used for the fluid flow description, and so with respect to that only we will be describing what happens to the fluid flow. So flow description is we can use these various techniques. And in steady state flow, the streamlines, streak lines and path lines are the same. So it will be, say, generally used as far as these lines will be used for unsteady state flow analysis. So now we have already seen the velocity field, and then we have seen how we can describe the fluid flow with respect to Eulerian description or with respect to Lagrangian description. So now the next topic, and also we have seen how we can describe the fluid flow, whether it can be fluid flow can be considered in 1 dimension, 2 dimension, 3 dimension, or steady state or unsteady state, like that. So now we will discuss the acceleration field. So acceleration is, say, most of the flow takes place due to acceleration, either due to acceleration due to gravity or the applied acceleration. So acceleration field is also another important, acceleration is also another important property as far as fluid flow is concerned. So in the kinematics of fluid flow, here we will discuss the acceleration field. So the particle acceleration, it is say generally here we can utilize this Newton's second law, which is given as force is equal to mass into acceleration. So say we have seen two methodologies of description of fluid flow. One is the Lagrangian method. So as far as Lagrangian method is concerned, so generally the fluid flow is described, say, with respect to time only. So the in the Lagrangian method, say, the acceleration is described as a varying of with respect to time. So that means a particle is, we are looking into that, and how it is moving or how it is behaving with respect to time. So here the space is not the major issue, since we are tracking that particle. So what happens for that particle with respect to time. So as far as acceleration field is also concerned, so here we will be describing, say, the acceleration is, say, with respect to time, mainly the variation is with respect to time. But as far as Eulerian method, which we have seen earlier, is in the Eulerian description we are considering a particular sections, and then we will be discussing what happens to fluid flow properties at that particular section. So here the acceleration field is concerned in the Eulerian description, we will be describing A is equal to A, X, Y, Z and T time. So the acceleration field is described with respect to the space X, Y, Z and time T. So and so as we know, the acceleration is time rate of change of velocity for a given particle. So in the Lagrangian method we can write acceleration A is equal to as a function of time, and in the Eulerian description we can write as a function of space and time. So here this figure shows, say, if you consider a particle, the path of a particular fluid particle. So for particle A, so here you can see that the particle path is like this. So particle at particle A at time t, so this is here, and then it is described with respect to x, y, z and then time t. So its position vector is represented like this with respect to the velocity component in x, y, z direction. So u a v, the velocity component in x direction, v a the velocity component, this v a is the magnitude of the final velocity, and this shows the velocity component in the y direction, and this gives the velocity component in the z direction. So particle A, the velocity is described as v a is the position vector of, say, r and t as described here. So v a is a function of r a and t, and that can be put as v a x a t, y a t and z a t as shown in this slide. So that will be represented like this, say, with respect to x, y and z and spatial direction and time t. So equation of acceleration is concerned. So in the the Lagrangian description generally we will be writing, say, with respect to u is equal to del x a by del t. So, the velocity is described as a now here we will consider the equation for acceleration. So, the velocity component in the next direction u is equal to del x a by del t, and v is del y a by del t, and w is del z by del t as shown in this figure. So, now acceleration is concerned, now the variation is with respect to x, y, z and t. So, that is why this partial is used here. So, finally, the acceleration can be written as acceleration is the derivative of the velocity. So, generally the acceleration is represented as say a is represented as dv by dt. So, if you consider the fluid flow at particular position point A, so the acceleration can be written here AAT is equal to dVA by dt, so which is the total derivative. So, that with respect to this UV description, so we can write now del VA by del t plus del VA by del x. So, that means the acceleration is now totally represented with respect to local acceleration as well as convective acceleration. So, here the acceleration for this particular fluid particle we will be considering with respect to the say time variation is with respect to local acceleration, and then convective acceleration with respect to the fluid flow, how it is behaving. So, that is what we are describing here. So, the acceleration is represented as the total derivative of the velocity vector with respect to time. So, that a is equal to dVA by dt. So, that can be represented as a local acceleration del VA by del t plus del VA by del x of dxa by dt. So, this is with respect to the velocity component in x direction u plus del VA by del y plus into dya by dt. So, this is with respect to the velocity component y direction plus del VA by del z plus into del z by dz by dt. So, this gives the total acceleration as far as the fluid movement is concerned. So, this one part is the local acceleration and other part is the convective acceleration. So, as indicated here in this figure. So, here this dxa by dt can be represented as u, and dya by dt can be represented as v, and dza by dt can be represented as w. So, now if we substitute finally, the total acceleration can be represented as shown in this slide as a is equal to del v by del t, which is the local acceleration, plus the convective acceleration is given as u into del v by del x plus v into del v by del y plus w into del v by del z. So, this is the general the acceleration as a vectorial representation. So, acceleration, since it varies with respect to space and time, so the direction and magnitude is there. So, acceleration we can represent it in terms of the x direction, y direction and z direction. So, with respect to this general description of the acceleration, we can write x is equal to del u by del t plus u into del u by del x plus v into del u by del y plus w into del u by del z. So, this expression is obtained directly from this general expression for acceleration. So, this is x direction acceleration is given ax is equal to del u by del t plus u into del u by del x plus v into del u by del y plus w into del u by del z. So, similarly, we can write the acceleration in x direction, y direction and z direction. So, as I mentioned, so this term here del u by del t is the local acceleration. That means, with respect to the x component, the acceleration in x direction ax is with respect to the velocity in x direction. What happens, that means local acceleration with respect to time, and then the other terms are called the convective acceleration. That means, with respect to the velocity u v w, how the acceleration takes place. So, these three terms are called convective acceleration, and the first term is called the local acceleration. So, similarly, we can write the acceleration in y direction as ay is equal to del v by del t plus u into del v by del x plus b into del v by del y plus w into del v by del z, and then acceleration in z direction can be written as del w by del t plus u del w by del x plus v into del w by del y plus w into del w by del z. So the acceleration in x, y, z direction is represented as a local acceleration term plus convective terms. So this is the general methodology used for the determination of acceleration. So this ax, ay and az are called the components of acceleration. Ax, ay, az are called the components of acceleration. So here you can see that in all this problem which we have seen so far, the analysis, the fluid flow analysis which we have discussed is mainly in terms of the without considering the force which drives the flow. We are not concerned now with the force, but later, say, this is the beginning as far as this topic is concerned. So later we will be discussing that also. So here the operator which we have discussed is the total derivative is generally. So now in the previous slide we have seen, say here the acceleration we have seen with respect to the x, y, z components. So with respect to this, the operator, we define the total derivative as d by dt is equivalent to the local derivative del by del t, that means with respect to time, and then u into del of del by del x plus b into del by del y plus w into del of del by del z. So this depends upon the properties. If it is x direction, this here will be putting u, y direction will be putting v, and z direction will be putting w. So these terms are called say the termed as material derivative. So these are termed as material derivative, and this describes the time rates of change for given particle. So the time rates of change for given particle is given by this total derivative termed as material derivative. So this we will be using in most of our derivations later stages. So the rate of change of for given particle or term as material derivative, the total derivative will be described with respect to a local term plus the convective term here uv and w. So further we will be describing the applications of the kinematics, fluid flow kinematics, and then further derivations, or we will derive various equations as far as fluid flow kinematics is concerned, and then that finally will be with respect to that one we will be proceeding to the fluid flow dynamics.